Okay, so this will just be a quick informal share on a tool that I've been working on for the past couple of weeks called FasterLit. And this is just something that could help you with your literature reviews if you're working in academia or you do research. And the idea is to automate all the tedious manual aspects of literature review and improve the search process. There are tools that do this already. So if you think those are great as is, then stick with them. This is more of just a pet project. So just to start off, I want to get on the same page about literature review. So obviously we all know what a literature review is, but just to break it down, we'll have some initial research question that we're interested in. Then we want to find some relevant papers to that question, and then identify gaps in the literature so that we can validate our new idea and start writing it. Or potentially, our goal was to identify useful methods that we could use in our research. The focus of my slides will be to talk through this middle part, basically how to find relevant papers to our research question or to our idea. And the first thing I want to talk about is why this process is so bad. You know, why did I even bother building this little thing over the last 2 weeks? So the process is really bad just for a few structural reasons. The first is in academic literature research, there's a lot of inefficiency in the actual search patterns just built in. So either you can, do default search where you just type a bunch of things, and here I've made these sort of purposefully bad, but either you type a bunch of things and you let the search engine extract the relevant keywords and do its own automated referencing and indexing, which usually just means that each one of these words that you've typed is treated as an independent thing to search for in the text, depending on if it's doing keyword search or a more advanced form of search. And this results in very broad results. So you'll end up with any paper that mentioned the word recommender or data set, so it'll become very inefficient. So maybe you'll get a hit that has everything in here, but if you're looking for very niche topics, chances are you'll instead end up with a mixed bag of very broad papers that don't pertain to your idea at all. The next type of pattern is exact match strings. This is where you put quotes around your search, and basically that's going to force the search engine to do exact match search. So it's going to give you exact matches of this string in the titles or abstracts of the papers that it's going to search. And this often results in the opposite problem, where it's too narrow and you end up with no results or very few results, because very few papers have that exact combination of words that you're looking for. The best approach is to use composite search strings, which is where you use the built-in and or operators and parentheses and the quotes to construct these more complex search objects that then get passed to the search engine, and you can basically mix and match different kinds of conditional logic and complementary logic to find exactly what you need. Now, these are good, but A, it takes a very long time to build them, obviously, and to think through how to structure them. And secondly, you'll probably still run into the issues that we talked above. If you use too many or statements, you'll end up with a very broad query. If you use too many and statements, you'll end up with no results, et cetera, et cetera. So it requires a bit of trial and error, and it's quite a time-consuming process. So all of these are quite annoying. Another inefficient search pattern is that basically, as you're looking for something on the left, for instance, for the search string, which recommender system performs best based on dataset meta features? This is a very broad search. This is like the idea you have in your head, but then maybe the literature has a totally different way of referring to these things. So there might be very technical jargon and specific terms that papers use to refer to these broad concepts that you're not aware of. And so when you type in your keywords, it's never going to match those papers. So this is a problem that's very specific to content-based search in academia because of the technicality of the language. And then the last issue is, once you do finally find a relevant paper that you like, you then have to look through all of its references and try and figure out which ones of those might be relevant, and then repeat that process over and over recursively until you end up with enough papers that you can actually use for your idea, or that you can use to identify gaps and decide if your idea is worth it. So it's quite a long and tedious process with many steps, and it's very manual. The better approach is to basically leverage AI, and this has come about in the last few years. Up until now, recently, lit reviews were a very painful and tedious process, and they could be very time consuming for a lot of researchers. And honestly, there's not a lot of value added, in my opinion, in that process. A lot of it is very mechanical and just figuring out what's been done. And a lot of the time is spent not on reading the papers and understanding what's been done. It's rather spent on trying to find these very few papers on your very niche topic. So a better approach is to use AI, at least, well, a debatably better approach. And there's lots of companies that have popped up, lots of little startups that have popped up around this. And generally, there are already tools that do this. I just want to make that clear. This is not like a novel tool that I'm building. There are some drawbacks to these, though. So first of all, not all of these do automatic search. So for instance, Lit Maps is a tool that's popped up a lot, but that does citation-based sort of network construction. So basically, it'll automatically plow through all of your, so basically you initially pass it some relevant papers. So you already have to have a couple relevant papers, and then it's going to parse through all of its references and construct this citation graph and identify new papers from the citations of those papers, et cetera, which is great, but it means two things. First of all, you already need to have a good idea of some relevant papers. And secondly, it's not going to identify new keywords, new papers that are outside of the original domain you passed. It's purely a citation-based search tool. And then we have things like Google Scholar Labs, which are great. At least I've recently tried it. It works pretty well. The issues are it just launched and it's still experimental. I don't think every user actually sees this on Google right now. The second issue is we don't really know where it's going to settle in terms of pricing because it just released. For now, it's just experimental, but they might actually eventually charge for it or set rate limits for how much you can use it, just like every other big AI company does. And lastly, you can't really do, as far as I know, proper chat interaction with it. So once you open a paper, you can't just ask it questions about the paper. You can ask it questions, follow-up questions, and it's going to keep expanding and trying to find more relevant papers. But you can't just have a sort of in-depth chat about the contents of that paper. So, some pros and cons. But overall, there are tools that do this or that are starting to do this. Another drawback, by the way, is cost. So obviously, these tools aren't free, as I mentioned. Google Scholar Labs is free, but I don't know if that's going to last. Whereas the other tools have free tiers, but they only give you unlimited access or extra features if you pay. So then, enter FasterLit, basically, this little project of mine. I'm just going to walk you through the back end here. So basically, I'm going to walk you through the actual search engine logic that I'm using. And then at the end, I'll give you a quick demo of the actual software and the UI. So the architecture of the search process is broken down in these 4 key steps, and I'll go through each individually now. So exploration is where we get an initial idea prompt from the user. So the user might say, oh, I want to predict which recommender system performs best ahead of time, right? We pass that to an LLM. So a large language model will process the idea prompt, and the LLM has a specific system prompt that tells it to deconstruct your idea into, I think it's 10 or 15 individual search strings with minimal overlap between search strings. And each one of these search strings can make use of the and or operators. It can make use of the asterisk for wildcards, depending on the search engine that we're using. It can use the parentheses to cluster things together, et cetera, et cetera. So it's going to construct all of these time-consuming, complex search strings for you, just based off of your original idea. And it's also going to inject literature-specific technical terms. If you gave it general and broad terms, it's going to automatically infer what the more technical terms might be that are actually prevalent in the literature. Once we have these separate search strings, we're going to ping an API, which in this case is the OpenAlex API. OpenAlex is a big open source and free, depends, but there's a free tier academic database that has lots and lots of papers and metadata about those papers. So each of these search strings goes through the OpenAlex API and basically executes its own little search, like keyword search, through the OpenAlex API, and then will return a certain number of relevant papers back as results. We cap this at 50 for each API call. So each one of these strings will result in 50 relevant, at most 50 relevant results. And then you just pool all of these together. So if we had like 3 search strings here, we'd have 50 each, so 150 total potential relevant papers as candidates. The next step is you pass each one of these papers through a sentence transformer. So this is going to embed our sorry, and when I say pass the paper, I mean pass the title and abstract of each paper to a sentence transformer, which is going to embed that text into vector space. So we're going to get a single vector representation for each paper. And this is done through a very lightweight sentence transformer that can run on very minimal RAM and CPU. It can do hundreds of these embeddings in a matter of less than a second or a second or two. And the idea then is, once we have this, we do this for the idea prompt as well. So the idea prompt also goes to the sentence transformer, also gets a vector representation in the same vector space, and then it's quite easy now to just do cosine similarity between these two vectors to get an overall relevance score, an overall measure of how related our candidate paper might be to our idea prompt. And then you want to repeat this over and over for every single one of the 150 potential candidate papers that we found. And then that moves us over to a refinement stage where we take the top 20 of these 150 papers by relevance score, and then we pass them to an LLM model. This will perform a secondary re-ranking where we take the papers and we give it, the LLM will have some domain knowledge and will be a bit more of a well-rounded expert in the field. It's not just a sort of mindless sentence transformer. And so it will be able to better decide which of these top 20 should actually be first and which should be 20th. And then we show the re-ranked papers to the user in the UI, and the user selects a subset of those that they deem relevant. And these relevant papers are what we call seed papers. So from these seed papers now, we're going to move into the snowballing stage, and we're going to say for each one of these papers that the user said are relevant, we're going to now construct a citation graph. So we're going to say, okay, what are all the papers that paper cites? And we track them all through the OpenAlex API. And then we're going to do the reverse, the complement. So we're going to say, what are all the papers that cite it? Right? And so now we cover all bases. We have this sort of 1 degree of separation graph of all the papers that might be related to this one. And the idea then is you just keep recursing. So now we'll go through each one of these related papers and do the same thing again and keep branching out with 1 degree of separation, and so on and so forth, until you get to some complex, locally directed graph like the one you see here that links hundreds of papers together based on their citations. And this is local in the sense that we've started from a few local nodes, which are the seed papers that the user gave us. And then we keep diverging and branching until we have a network. Now, I've simplified it a little bit. There are extra criteria here. You can see how if I did this exactly as I said, we would very quickly, like within 1 or 2 layers, get to an exponentially large graph. So we get to something that's really unfeasibly big. So there's a specific branching logic that decides when to branch, which nodes to branch from, sets maximum depths, and et cetera, et cetera. But I'm not going to go into that right now. So you end up with this citation network, essentially, which gives you hundreds of relevant papers in addition to the seed papers that the user selected. Now we enter the final stage, which is re-ranking. So for each one of the papers in this citation network, we again pass its abstract and title through the sentence transformer, and we get a relevance score to our original idea prompt. Then we also, though, look at the paper in its graph context and we say, well, what else is interesting here? Well, we can calculate some network scores. We can say, okay, well, this paper is really interesting because it has been cited a lot, or because it's been cited by other important papers, that's PageRank, for instance. This paper is important because it bridges 2 very dense clustered networks, like 2 different clustered parts of the graph. And so it's like a bridging paper that connects two different fields together or something, et cetera, et cetera. So you can calculate lots of these different network-based scores that to infer to add additional sort of explanatory power to our similarity matching, in addition to just content-based sentence transformer-based matching. And then we come up with a final re-ranking score. And the final re-ranking score is just some weighted average of the relevance score and the network scores. And then this is what we use to finally decide which papers are most relevant and to show to the user. So we'll show them the full hundreds of papers in the citation network, but we'll rank them according to the score. And then I forgot to include in the slides, but there's again a little step where we surface the top 20 to an LLM and then ask it to rank those. And then those are the top 20 that we show, but we still show the full rest of them according to the re-ranking score. So that's the gist of how the actual architecture works. And now I can show you how all of it works in practice through a little demo. We can start using the application by pasting in a research question or a paper idea here. And I'll just paste this pre-prepared one, which is basically just asking how different recommender systems perform across different domains, and if we can pre-select a good one. Once you're ready, you can click Find Related Papers, and this will start the search process that I talked about in the presentation. So we're going to go through each of the steps that I outlined, and this can take anywhere between 20 seconds and 2 minutes, depending on the search complexity. So I'll probably just skip ahead here in a second and then meet you back when it's ready. Great, and we're back. So now we're being displayed the candidate papers that might be most relevant to our initial research question. And you can see it did a pretty good job. We have impact of data characteristics on recommender system performance. We have some papers talking about how different recommendation algorithms perform differently depending on user, recommendation context, etc. So this is roughly what we were after. The idea here is now me, the user, will select the most relevant of these. There's about 20 of them, as we said. Let's just pick a couple to make this simple. So this one seems relevant. This one seems relevant. This one might be relevant. Let's just go with it. And once we're happy and we've selected the things that we think are relevant out of the 20, we can click Build Citation Network. And this is now going to start the snowballing phase of the presentation slides, where we build a citation graph network from these 3 seed papers that I selected. So again, this can take anywhere between 20 seconds and a couple of minutes. So I'll just meet you back when it's ready. And we're back. So now you can see we have this full breakdown of results. There's around 300 papers that were retrieved and ranked. And this will basically show us the full network ranked from most to least relevant paper. And if you click on each one of the papers on the right, you'll have a full breakdown of all the information you need, title, authors, publication year, abstract. And if you want to look at this paper in full, you can just click on the View Paper button, which will take you to the website that hosts it. Now, in addition to that, we have 2 extra buttons, Chat and Summarize. And these allow us to, if I click on Chat, open an actual chat window so that I can ask AI questions of this recommender system. So for instance, I might say, tell me a bit about this paper. And then it's going to send that and give me a little summary and so on and so forth. So obviously you'd ask it more meaningful questions. And you can keep chatting back and forth. Once you're happy with what you have, if you want to, you can copy the entire chat or save the entire chat as a local markdown file on your computer. The chat will also display the original copyright of the paper, and it will only allow you to have this automatic chat with permissively copyrighted papers that you can transform and redistribute because it's automatically fetching the PDF file and the full contents of the paper. Otherwise, if I click on, for instance, another paper that might not have the same permission, you might get a warning like this one, which just says, we couldn't verify that this has a permissive license, but if you think we're wrong, or if you're the author, etc., feel free to upload the PDF, and then you can have a chat about that PDF as normal. There's also a summarize button, which, again, if I click now, it's going to give me an error, but it's going to automatically summarize the paper according to a default system prompt. And then the idea is all of these things remain stored. So if I now go back to that second paper I was on and I click on chat again, I still have my full chat conversation. This persists between application sessions, and same with the summary if I were to create one. And so basically the idea is, you can go through each of these results, move interactively, have chats, summarize the content. You can save the summarizations or the chats. And then also there's easy filtering options. So you can bookmark any paper that you like, or you can remove the bookmark if you don't like it. Then in the top right here, you can only show the bookmark papers so that it's easier to navigate things. And if we go back to the main view, if you want to look back at a previous search, you can see on the left here, it stores each one of your previous paper searches. And if you want to save it because you want to take it off of the application, you can just click on the three dots and click on download. This will open a download window in your folder. In your drive, and then you can just download the entire thing, like all of these results, including all the chat histories and all the summarizations and everything that you've ever done with it, as a big zipped folder. Another useful thing is you can decide whether you want to use a remote AI or a local AI for the chat and summarize functions. So if you go to the bottom left in the settings, you can choose sort of either to use OpenRouter if you want to use a remote AI, or you can select Olama and then specify your local server host URL, and then specify the name that you want to use, of the model you want to use. The last thing I want to show you is you can do the exact same thing that I've just done, except you can start from a new paper or a number of papers that you already have and that you think are relevant if you don't want to start from a search prompt. So I'll just start by adding some papers, and the way you do this is you click on the Add Paper button, and then here you type the title of the paper. In this case, I'll just paste one that I had ready, press Enter, and then that's going to give you the nearest matches. In this case, I wanted this paper. That's going to add it to the seed papers, and then you can keep adding as many as you want. For instance, we can add a second one. Again, I'll just paste one that I had ready, and click it and add it. Now, when we're happy, we can click Find Related Papers, and this is going to start the same exact process as before, except it skips the searching stage and it skips right to the snowballing stage from the slides. And this, again, is going to take 20 seconds to a few minutes. In this case, we don't really have to wait and see because we got the gist of it. So that's all I wanted to show you.